Now we're going to talk about conduction, convection, and radiation. They're all different ways that energy can transfer. So, if you say conduction, and I guess not electrical conduction, but heat or thermal conduction, is going to be when the energy transfers from molecule to molecule because the molecules bump into each other or are touching each other. Right? So basically conduction would be heat transfer through touch. And some materials are better conductors of heat. So that's when we can come back to my brick and carpet floor. And both the brick floor and the rug are the same temperature and they're both colder than your foot. But when you step on these two different surfaces, one feels a lot colder because this is a better conductor of heat. It can take the heat out of your foot faster. The conduction rate for brick is 44 times higher than cotton, than something like a rug. So it's going to feel a decent amount colder when you step on a brick floor or a tile floor. So here's just a quick video illustrating this idea. So here we have a hot region, and imagine this as being maybe a metal bar, and these dots would represent the different atoms in the metal bar. And so the atoms are in contact with each other, and as the heat is applied to the bar, the atoms closest to it heat up, but then they bump against their neighbors, and eventually that heat, that energy, transfers down to the other side of the bar. And so the energy of the flame is conducting to the other side. The heat is getting to the other side. All right, for convection, that is transfer of energy because the material itself is moving. So in the previous example, those little atoms in the bar, they bounced around, but they stayed in their own little spot. Right here we're talking about maybe fumes coming out of a smokestack, and the fumes in the smokestack are hotter and they're less dense, and so they would rise upwards. And so the fumes, the exhaust gases, rise upwards, taking that energy with them. Here's just a quick example. Let's say that it's a sunny day and the sun is shining, heating up the ground. Well, that's also going to heat the air right above it. So the heated air that's near the ground will tend to rise upwards. As air tends to rise upwards, it also has time to cool off, but it also expands, which we'll see in a little bit will cause it to cool off more. So as it rises, it cools. As it rises, it cools, and eventually it reaches a certain height in the atmosphere. And that height depends on the temperature and the humidity that day. And when it reaches the right height, which is the right temperature, that the water vapor that was in this warmer air can turn back into droplets. And that would be condensing, from going from a vapor to liquid droplets. And that is why we would get clouds. And I love the days where you can see these little puffy cumulus clouds, and you can see that they all share this flat bottom. And it took me a while to figure out in school why they all have the same kind of height to their flat bottoms. That's where the right temperature is and the right humidity is for it to change from water vapor to condensing. Now, we had said in order to boil a liquid or to evaporate a liquid, that takes energy, that takes latent heat. Well, when you're going from a vapor to a droplet that's condensing, that releases heat. So in the process of making a cloud, it actually heats the surrounding air. Eventually, though, the surrounding air will cool off. It'll mix with the other air. It'll give off some of its energy to space, and it would sink back down. And so convection is just this movement of air, taking the energy from the hot region and moving it up or higher up in the atmosphere so it can cool off. All right, I left a little note here about the if air rises to a higher altitude, it has to expand, and that the expansion itself takes energy and cools the air, but we will come back to that in another section or two as well. All right. Another way that heat and energy can transfer from one location to another location is through radiation. And there are lots of different types of radiation. The word radiation really just means travels outward in a straight line. And so one type of radiation is really just light. All right, so what we're going to talk about right now is just light energy. The fancy word for light is electromagnetic radiation. And I can tell you why. Light is really just a wiggle in the electric and magnetic fields. So there's an electric field all around you and a magnetic field all around you. And when it wiggles, it's light. And that wiggle, once it happens, travels outward in a straight line. And there's different energies of that light as well. Radio waves are low energy light. Microwaves are low energy light, but we found out that they're really good at heating up water. Infrared light, and so all of us are giving off infrared light right now, so I tend to think of myself as an infrared light bulb. Visible light, ultraviolet light, that can give us sunburns, X-rays, and gamma rays. And the ultraviolet, the X-rays, and the gamma rays are all strong enough to damage your DNA and possibly lead to cancer. One of my friends once was saying how they had gotten rid of their microwave because it was a source of radiation, which is technically true, but it's not the type of radiation that is scary like X-rays or gamma rays or ultraviolet to me. What microwaves would do, at least to my body, if I was exposed to them, would be to heat up my water molecules. Now, obviously, too much warmth would be deadly, so, don't put yourself in a microwave. So just due to an object's temperature, it will give off some light. Maybe you can see it with your eyes, maybe you can't. But hotter objects would give off more light, so brighter, and also at higher energies. So instead of maybe at infrared, maybe at visible light. Two examples. The surface of the sun is 10,000 degrees Fahrenheit. It emits mostly visible light. And so here's a good way to think about how the radiation can transfer energy. The sunlight brings energy from the sun to the earth through radiation, through light. My other example is skin temperature, which is 91 degrees Fahrenheit. And that gives off mostly infrared. Our skin is cooler. We're not going to glow red or orange like a light bulb. Our skin will just reflect some light. Now, if I imagine sunlight coming from the sun and coming to Earth, all right, we have that light energy. All right, so now I can imagine maybe some light energy coming at the Earth again from the sun. And that can be absorbed or reflected. Like if the sunlight hits the clouds on its way towards the Earth, it can just be reflected away and go back to space. But if the light shines onto a dark patch of ground or some blacktop, much more of that energy will be absorbed. So if you want to reflect light energy away, you might choose white, like a white shirt or a white wall or a white roof will help reflect more of the light, and then your material will not get quite so hot. Whereas if you do want to absorb a lot of energy, like maybe it's wintertime, you could use black. Black walls, black shirt, that absorbs more light. Now, I don't really want to talk through the definition of solids and liquids and gases, even though I wrote up their definitions here. So if you want to, you can pause it and quick read my definitions. But these are just broad categories anyways. There are some weird things that happen that aren't clearly a solid or aren't clearly a liquid. So these are just kind of general categories. But I did want to point out that plasma is also another state of matter. Instead of just a solid, liquid, or gas, a plasma is what you get when you heat up a gas. And you heat it up hot enough where some of the electrons can be removed from an atom. And so a plasma is an electrically charged gas. So like maybe I had some helium gas. And so a helium atom would have 2 protons in the middle, which I didn't draw, and 2 electrons outside of it. And this would be neutral, because it would be positive 2 from the protons and negative 2 from the electrons, so overall it would be 0. So this is not electrically charged. But if you heat it up, heat it up, heat it up, basically you take one of these electrons and you rip it off. So now they're separate. So now you have a positive thing, and it can move off and do its own thing. and you have the negative electron, and it can go somewhere else and do its own thing. So now it is electrically charged. So now your hot gas would be called a plasma.